Hello and welcome back. Today I'm going to tell you what to do when, or put in different terms, I'm going to tell you which type of statistical analysis you're going to do under which circumstances. And this is quite an important topic, as you will find out soon. Now imagine that you've collected your data and then you want to plot these data in XY space. So we set up a diagram, and this diagram has an x and a y-axis. The x-axis contains the explanatory variables, and the y-axis contains the response variables. Now, which types of models will you encounter? The first type is probably what you think of first. This is where you can basically plot some dots in this diagram here. And whenever you have dots in this XY diagram, you're basically performing something like a regression analysis. And this is where the explanatory variables are continuous. That means they can take on any values, be it either integer values or real values. So whenever the explanatory variable is continuous, we're going to do something like regression and other types of models. However, there's another situation that is maybe not what you thought of first, and this comes about when the explanatory variable is not continuous. What could that be? It could be, for example, that the explanatory variable is a so-called factor, and a factor consists of levels. For example, you could have low and high levels of fertilizer in an experiment on plant yield. Now, the graph that you would plot here usually looks a bit different. You usually show something like an estimate of central tendency here, for example, the arithmetic mean. And whenever you do that, you end up with a bar chart here. And potentially the bar chart also contains some estimate of variability of these measures of central tendency, as shown here by error bars. Now, what type of model are you going to use when the explanatory variable is a factor? Well, here this is what you usually would call an analysis of variance or ANOVA. Now, these are the two very basic types of statistical analysis that you can do. However, be reminded that these two things here are actually two different variations of the same topic. These are all so-called linear statistical models. It's just that we use slightly different codings of our explanatory variables when we analyze these data. So it's essentially everything we're doing in parametric statistics is going to be related to linear statistical models. Now let's look at such a linear statistical model in greater detail. So what is a linear statistical model? You will have to use formulae now, simply because you want to understand what's happening. And one formula that may be familiar for you is the formula for a straight line relationship between an x and a y variable. So whenever you have a straight line in such a diagram here, you can describe this line using a straight line equation y equals a plus bx. So this is not yet a linear statistical model, but it leads us there. Now, what are these parameters in this model? A and b. These are the parameters. And a is the value of y that the model assumes when x equals 0. So if x equals 0, then we have y equals a plus b times 0. So y equals a. So if this is 0 here on the graph, then a is the value where the line intersects with the y-axis. And this is the so-called intercept. And the second parameter, which is the b one, this is the so-called slope. And the slope is usually estimated as delta y over delta x, meaning that you take two values of y and you take two values of x. Divide these differences by one another and you get the slope of the line. As I told you, this is not yet a linear statistical model, but it leads us there. Now, the formula for a linear statistical model looks very similar. It looks like that. Y equals beta naught plus beta 1x plus epsilon. That's what the principal formula looks like for a linear statistical model. Now there are different parameterizations, different names of variables and parameters, but you recognize here now that these two terms here, the beta naught and the beta 1, these are the intercept and the slope. Now there's something new in here, which is the epsilon. Epsilon, this is the errors that are usually estimated as being the residuals in your data. Now they are not really observable, but they will be present whenever you have, for example, measurement errors. Now this epsilon is important because it shows us that not everything is perfect. Not all the data points will lie perfectly on the regression line. So if all values would be lying on this regression line, then the residuals would be 0, and we would be left with y equals beta naught plus beta 1x. Now, because there is variation around the line, we usually need to use this formula with the epsilon term for our linear statistical model. Now, this is a linear statistical model which is just for one explanatory variable. And we will soon encounter statistical models where we expand the formula for more than one explanatory variables. But this is something for the next sessions in our lecture series here. For now, I just want to tell you that the intercept and the slope will also be there in other types of models, especially in models where the explanatory variable is a factor. But we will encounter this later on during the lecture series. Thank you for listening to me, and I hope to see you back again soon.